Okay, so in this video, I'm going to go over some of the basics of working with continuous random variables, and in particular, I'm going to focus on uniformly distributed continuous random variables. Okay, so if you remember working with this type of random variables before, perhaps from advanced statistics, and if you feel comfortable with describing the density functions for uniform random variables, calculating expected values, updating and calculating conditional expected values, then you can skip over this and maybe just read the technical appendix in the lecture notes. But we're going to rely on this type of technique when we're studying Akerlof's model. So it's worth going over now if we're not 100% comfortable with it. Okay, so so far in the course, when we've worked with lotteries and so on, we were talking about random variables with that only take finitely many values. Okay, so we might call this a discrete or even a finite or simple random variable. Okay, and an example of a uniformly distributed one, so a discrete random variable with a uniform distribution, could be something like our rolling the dice example from a previous lecture. Okay, so the support of a random variable, okay, when we say the support, we mean the set of values that this random variable can take with positive probability. Okay, so when we were talking about the dice, the support, or the set of states we called it, were the numbers 1 to 6. Okay, so they're all of the states that can occur with positive probability. Okay, and then so the fact that it's discrete meant this is a finite set, and the uniform distribution here is simply to say, well, the probability of number I is just equal to 1 over 6 for all I equal 1 up to 6. Okay, so that's what makes it uniform, the fact that every particular outcome has the same probability. Okay, now when we work with continuous random variables, and let's say continuous uniform random variable. Okay, what do we mean by continuous? Well, the support, the set of values that this random variable might take with positive probability, for us, we're going to label it an interval A to B, okay, where A is less than B, okay? So it's a closed interval. I could draw a diagram here. All of the points between A and B are possible values that our continuous uniform random variable might take. Okay, now how many points are in this interval? If I wanted to do something like each point has probability 1 divided by the number of points, well, there are far too many points in this interval. In fact, there are uncountably infinitely many. This is what we would call a continuum. Okay, so when we're dealing with a continuous random variable, rather than talking about the probability of specific values that the random variable might take, what we do is we talk about a density function, which is going to capture the same idea as a probability number, but a density function is going to capture some sense of weight being associated with a particular value. But we're going to talk more importantly about the kind of regions that this random variable might take. Okay, so I might talk about the probability that it lies between maybe 2 points C and D, something like that, rather than saying what's the probability of C, what's the probability of D. I'd say what's the probability that this random variable lies in this interval, C to D. Okay, see, a point has 0 length, which is why we can't measure, why the probability of a specific point has to be 0. But I could talk about the probability of a certain interval. So that's how we work with this. So how do we work with a continuous uniform random variable? So let me just, I'll describe the density function, and then I'll explain what it means. So the density function, let me draw a diagram of it. So it's going to be essentially a straight line. That captures the idea of this probability weight being uniformly distributed across all of these outcomes equally. Okay. And then the height of this box, well, essentially we want the area of this rectangle, okay, to be equal to 1. So that rectangle has area equal to 1, okay? So what must the height be? B minus A is the length, so 1 divided by B minus A must be its height, okay? So the density function, which we always write little f of x, is equal to, it's going to depend on x. It's going to be 1 divided by b minus a. If a is less than or equal to x, less than or equal to b. Okay, so if x is somewhere in this interval we call the support, then the density function tells you it is equal to 1 divided by b minus a in that interval, and then it's equal to 0 otherwise. Okay. So what does this mean? Well, the fact that the area is 1 here, in some sense you can see that the total area underneath this density function is 1, which is saying that the probability that our random variable takes a value in this interval is equal to 1. Okay. So if I wanted to calculate, for instance, the probability that our random variable capital X, okay, so capital X is a random variable, it's continuous, uniformly distributed. What's the probability that it lies in an interval C to D? So that C is less than or equal to X is less than or equal to D. Okay, how would I calculate that probability? I essentially look at these 2 points, C to D, and then I calculate the area of underneath the density function between those 2 points. Okay, so in general, if I have a density function that I can integrate, I would be integrating between C and D the density function f of x dx. Okay, that's how I would calculate the probability that our random variable takes a value in the interval C to D. Okay, now for the case of uniform random variables, continuous uniform random variables, this is really simple because I can just look at this and think, well, this area is a rectangle. Its width is C minus D, and its height is 1 over B minus A. Okay, so I can immediately calculate an expression C minus D, D minus C. D minus C divided by B minus A, and this is going to tell me the probability that our random variable takes a value between C and D. So now let's use this idea of a density function to calculate the expected value of a continuous random variable. Okay, so for the uniform, a continuous uniformly distributed random variable with support, we just labeled an interval A to B. Okay, now when we work with one sec, let's just write the density function f of x is equal to, it's either 1 divided by b minus a if a is less than or equal to x less than or equal to b, and 0 otherwise. Okay, so there's our density function describing the probability of the distribution of probability for this random variable. So now when we calculate expected values, if we think about the discrete case, how do you do this? It's basically a weighted average, right? So in the discrete case, you would say, well, the expected value of a random variable x would be this. I would add up, I would multiply each possible value x by its probability, px, and then I would add up for all the x that belong to the support of x. Okay? So there are other ways of writing that, but that's the basic idea, that you are adding up weighted values. So you multiply each outcome by its probability for all of the outcomes that are possible, and then take that weighted sum, gives you the expected value of the random variable x. Now, for the continuous case, of course, the probability of each specific value, p of x, would be 0, and we're taking a continuous sum. So we're going to use the density function. So for us, for the continuous case, I'll just put continuous random variable. The definition of expected value would be this. You take the integral, I suppose I could put from minus infinity to positive infinity, or if I know the support, I could just put the support as the bounds of the integration. And then I'm going to take each value x and weight it by the density function f of x, and then I vary x across that interval. Okay, so it's capturing exactly the same idea as the discrete case. We just have to use this idea of a density function when we're calculating expected value for continuous random variables. Now, what about uniform random variables? So if I look at this diagram here, all outcomes between A and B were equally likely. So essentially, the easy way to remember is that the value in the middle, A plus B over 2, is going to be the expected value. Okay, so for a uniform random variable, the expected value is just the middle of that interval, A plus B divided by 2. Okay, now you could prove this by integrating the density function if you like. So that might be a nice exercise. This integral would be equal to, I take x and multiply it by the density function. So I would get x squared over 2 multiplied by 1 minus ba, 1 over b minus a, and then the b. So I take this expression, evaluate it at b, evaluate it at a, and then deduct the second from the first. And if you do that, you'll get that this is the expected value for a uniform distributed random variable. Okay, so the easy way to remember it, you're going to need this general definition of expected value later on, especially when we work in auction theory, where we're going to have several kind of distributions derived from the uniform distribution, but that are different. So we're going to need to use this later. But for now, you can just remember, I just take a uniform random variable, I just look at its middle value, a plus b divided by 2, and that's the expected value of this uniform random variable. Now that we know what uniform random variables are and we know how to calculate the expected value of a uniform random variable, a continuous uniform random variable, how do we handle information? How do we update uniform random variables? So this is quite simple. So suppose we start with a continuous uniform random variable. So one way of writing this is just to write that x is distributed uniformly on the interval a to b. Okay, so that's a shorthand for what we were writing out. X is a continuous random variable uniformly distributed with support the interval a to b. This is a shorthand. Now suppose we're given information. So suppose we are told, or that we have reason to believe, that x actually lies between two values, c and d, so that c is no greater than x is less than or equal to d, okay? Where c and d are in between these a and b values, okay? So suppose we're told that our random variable that we initially believed would take values between a and b will in fact take a value between c and d. So how do we handle that? Well, essentially we find the c here, and let's say d is here, okay? Now this is no longer the density function. We need to update, but we know it's a uniform random variable. So we essentially just form a new uniform random variable with this density function, and this height is obviously 1 d minus c. Okay, so that there is now area 1 under the new density function that we've updated from the initial one. Okay, so updating these continuous uniform random variables is a very simple task. And now that we've updated it, what's the expected value? Well, we could say the expected value of x conditional on the information that x lies between the values c and d. So we can condition on that information we're taken as given, and we could do an integral and calculate it, but our trick is just to look in the middle of this interval. So it's going to be c plus d divided by 2. Okay, so that's how we would calculate the conditional expected value, conditioning on the fact that x takes a value between c and d, which are between these values of a and b. Okay, now one important case we're going to look at is when we have a parameter. So let's suppose we wanted to calculate the expected value of this x, conditioning on the information that x is less than or equal to, say, some number e. Okay, so in this case we're just given an upper bound, so we know that a is still the lowest. Okay, so what does this thing equal? Well, let's be a bit more careful about this, because it's going to depend on this e, right? So let's take up a bit more space. So the expected value of this random variable conditional on the assumption that it's less than or equal to e would be, well, if e is down here, okay, then we already assumed that it's going to be greater than a, and then we're told it's being less than a. So in a sense, we're conditioning on something that we believed wouldn't happen. So we'd say that's not defined if e is less than a. Okay, so essentially we'd be trying to find the expected value of an empty set, which you can't do. So given that we believe x is already lies between a and b, if we're then told to condition on it being less than e, our expectation's not defined. What about if E is in this interval between A and B? Okay, well then I would update okay, I'd form a new distribution like this, which has area 1, and I'd look in the middle, so it would be A plus E divided by 2 if A is less than or equal to E is less than B. Okay. Now, what if it's greater than B? What if E is all the way over here? Okay. Well, we already assumed that B is the highest value that X will take. Okay. So if we're conditioning on the fact that it's less than something greater than what we already assume it's less than. Okay, that's a bit of a mouthful, but we already assumed it's less than or equal to B. That implies it's less than or equal to anything greater than B. Okay, so if E is greater than B, okay, then this information isn't going to change our assessment. So the expected value would be A plus B divided by 2. Okay, so then it wouldn't depend on E. Okay, so this idea of looking at the conditional expected value, conditioning on it being less than or equal to some value, is going to be very important. In particular, as we're studying Akerlof's model, we're going to be looking at expected revenue, conditioning on something not exceeding the certain wage level. So this type of construction is going to be very important.